Have you ever really stopped to wonder what an AI model truly remembers from all that data it's trained on? Well, it turns out a new paper might have just cracked a universal secret, a hidden signature that basically screams when a model has memorized something, and believe me, this has some pretty profound implications for the entire future of AI.
Okay, so let's just dive right in, because this chart right here is where our whole mystery really kicks off. So, researchers built this attack specifically to sniff out memorized data. And get this, they trained it only on transformer models. But look at these results, it's wild. The attack actually works better on completely different architectures it's never even seen before, like Mamba, RWKV, and recurrent Gemma. I mean, how on earth is that possible?
So this isn't just some weird academic quirk. It's a major AI security puzzle. And solving it, well, that reveals something really fundamental about how all of these different models learn, and it has massive consequences for data privacy, for copyright, you name it. So let's unpack this together.
To really get the breakthrough here, we need a little bit of context first. For years, there's been this sort of cat and mouse game going on between AI builders and security researchers. And it all revolves around one big question. Can we actually prove what specific data an AI has memorized?
The main tool in this whole game is something called a membership inference attack, or MIA for short. And its goal is actually pretty straightforward. You feed it a piece of text, and it tells you, yep, this was in the training data, or nope, never seen it. And this is absolutely crucial for things like privacy audits or for creators who are trying to figure out if their work was used to train a model.
Now, what's really cool is how these attacks have evolved. The old way was all about these handcrafted rules, basically built on human hunches. You can think of it like a security guard who just has a fixed checklist. But this new way, the learned attack, is a totally different beast. It's more like training a detective to spot these universal patterns of suspicion that a human would just completely miss.
And that right there brings us to the big breakthrough in this paper. They figured out how to build the first truly scalable learned attack for our massive modern language models. This really brings the whole field of membership inference into the deep learning era. So the method is called Learned Transfer MIA, or LTMIA. And at a high level, it's actually really clever. It takes a model that's been fine-tuned on some data and compares its outputs to the original, pre-trained version. It's basically looking for the tiny, subtle changes that happen when a model commits something to memory. So let's break that down real quick. First, for every single word in a sentence, it grabs a bunch of statistical features from both models, the original and the fine-tuned one. Second, it zeroes in on the difference between them. How exactly did the model's predictions shift? And then finally, a separate small AI classifier looks at that whole sequence of differences and makes the final call. Member or non-member?
And the results? They are just staggering. In a super realistic scenario where you can only afford a tiny 0.1% false positive rate, this new method is 2.8 times better at finding memorized data than the next best thing out there. This isn't just a small step up, it's a massive leap forward. Okay, so that brings us all the way back to our puzzle. We now know what this attack is, but why in the world does it work on models it's never even been trained on? Well, the answer is the discovery of a universal signature of memorization.
Right, here's the absolute key. The paper argues that the fingerprint of memorization isn't buried deep in the model's internal wiring. It's not in the attention mechanisms or the state spaces. No, it's in the statistical pattern of its outputs. In other words, fine-tuning leaves this telltale sign, and it turns out that pretty much any model trained the same way is going to have that exact same sign.
And boom, this chart right here is the proof. Just look at those green bars. For all four of these completely different architectures, the most important clues are those comparison features, the ones that measure the change from the pre-trained state. That right there is the universal signature. The attack works because it learned to look for this signal of change, not a signal tied to any one architecture.
I mean, really think about that for a second. These models have practically nothing in common under the hood. One's using attention, another's using state spaces, a third uses linear recurrence. The only shared thread is the fundamental training process, gradient descent on cross-entropy loss, that nearly every modern language model uses. This means the vulnerability isn't some bug in transformers, it's a fundamental feature of the learning process itself.
And this chart reveals one of the secret ingredients to the attack's incredible power. What it shows is that training the attack classifier on a bunch of different kinds of models forced it to ignore all the model-specific quirks and learn only that universal signal. As you can see, diversity was way more important than just piling on more data from a single model type.
So,
What does all this mean? We found this universal signature of memorization. So what? Well, the implications are actually pretty huge for pretty much everyone building or using these AI systems.
For developers, it's kind of a wake-up call. You can't just invent a new architecture to fix this privacy risk. The problem goes deeper. For the people on the defense, the auditors, this is a game changer. You now have one single powerful tool that can check for memorization across this huge range of AI models. And of course, for copyright holders, this gives them a much more accurate way to see if their data was used to fine-tune a model.
And all of this leaves us with one big, final, and kind of provocative thought. If this signature of memorization is so baked into the very process of learning that we use for AI today, can it ever really be erased without just crippling the model's ability to learn? It really forces us to ask the question, is leaking information just a fundamental, unavoidable cost of learning?